Example 2 is what is the electric field from an infinitely long line of charge with charge per unit length lambda. And lambda here is uniform. That's given in the equation, but I had not written that out here, but consider lambda to be uniform. Now, why there must be an electric field because of this? So this line of charge is infinitely long, but I'm going to look at a section of this charge, okay? So here you've got this nice little line of charge, and because it is a line of charge, there will be some electric field coming out of it. So it can be some random electric field like this, where it's in this direction here. It's a different direction here. It could be like this, like this. But I'm going to use symmetry arguments to convince you that the electric field is actually like this. Electric field is actually like this, where it's coming out because we've assumed that the charge distribution is positive and it makes 90-degree angle with the line of charge. So this is the electric field, right? How do I know that this is the case? So if we look at this guy, let's say, I'm going to quickly copy this, paste it here. So let's look at this guy. Okay, imagine there's a tiny charge dq here. Okay, and there's another tiny charge dq. Because it's a point charge, it's a really tiny point charge, there is electric field coming out of it like this, in all direction. Like that. The same is with this charge. This is charge number 1, this is charge number 2. So I'm just looking at two tiny charges in the line of charge. Same thing is happening here, electric field coming out like this. Okay. Now imagine an electric field line from dq1, which is like this. Okay. It is some electric field line that is not making 90 degrees angle with the line of charge. So this is some theta which is not equal to 90 degrees, right? So if I look at this one and I imagine breaking down this electric field line into its component, so I'm going to call it EX and EY. I'm going to do the same. So there's like an electric field which is pointing in this direction, which makes angle theta again. So it will have EX component and then EY component. So I'm looking at these two charges, charge number 1 and then charge number 2. And I have broken down this electric field which was not making 90 degrees with the line of charge into its X and Y components. So immediately I see that the electric field's X direction for part A cancels the electric field's X component from part A, for charge A cancels the electric field's X component of charge 2. And because they're same equal charge, these two electric fields components, they cancel each other. So all you are left with is electric field in the Y direction. Okay, like if this is dq1, so dq1 and then dq2. So all you're left with is electric field in the Y direction. Now, same thing will happen with every pair. You can take a tiny dq here and then tiny dq here. Same thing will happen. So all the pairwise cancellations will happen, and after that, in the end, you'll just have electric field which will be pointing in the Y direction. Okay. So now we have established that if the unit the charge density is uniform, that means you can have this pairwise cancellation of X components of charges in this line of charge, and you're left with only Y components. Okay, so we know for sure this electric field makes 90 degrees with the line of charge. So that's one thing to really grasp here, and that is electric field lines coming out of the line of charge, which is uniformly charged, is perpendicular to the line of charge. Now, what we need here is electric field, and we need to actually calculate the electric field. So I'm gonna instead of calling it EY, I'm just gonna call E because there is no EX. Okay, so E is the electric field. Now I'm gonna quickly copy this. So I have this guy right here, and so this is the electric field. And I'm gonna imagine a Gaussian surface. So if you look at a line charge, the best Gaussian surface here is from the symmetry is a cylinder. Okay, so I'm imagining a Gaussian surface like this. That's my Gaussian surface. It has radius r, and its axis is going through the line of charge. It is radius r, and I'm going to call this section of this really long wire capital L. Okay. Now Gauss's law tells us that electric flux is equals to Q enclosed over epsilon naught. Now this is important. As soon as you write it down, you need to understand what you will be doing in left hand side and what you will include in right hand side. So left hand side is phi E, which is just E dot dA, and right hand side is Q enclosed. We're going to get to it later. That is this. Now electric field here, I'm just going to do a dot product E dA cosine of theta, where dA, always remember, as I know a lot of us get confused with what area we have to integrate, what area we should take. When you talk about electric flux, you always talk about electric flux through the Gaussian surface. So our Gaussian surface is this right here. That's Gaussian surface, right? So that means that electric field, we have established that is perpendicular to the curved surface area. So if I think about a small tiny area here, electric field lines are perpendicular to it, right? So that means theta equals to 0 degrees because area vector is also pointing here and electric field is also pointing here. So this implies that theta equals to 0 or cosine theta equals to 1. And I also know that this electric field is uniform and it only depends on the radius, on the distance from the positive line of charge. So that means that I can take that out of the integration and I can just do this, and cosine theta equals to 1, and this is equal to Q enclosed over epsilon naught. Now this side right here tells you that you have to incorporate all the sides and all the area of the Gaussian surface. But I'm going to only take the curved surface area, not the sides. Right, not these sides. The reason is that I can clearly see that electric field lines are in a way which is where these electric field lines are making 90 degrees with the line of charge. That means none of them are going through the sides. See, none of them are going through the sides. That means flux through the sides is 0. I only have to take care of the curved surface area. This implies there's going to be area, curved surface. Okay, that's going to be Q enclosed over epsilon naught. Now, curved surface area of a cylinder of length capital L and radius r is given by 2 pi r L. So I'm left with Q enclosed over epsilon naught. Now we need to figure out what Q enclosed is. So Q enclosed is the charge enclosed inside the Gaussian surface. The charge enclosed inside the Gaussian surface. So if I look at the Gaussian surface right here, the charge enclosed here is whatever we have charge here, and that is just the line charge of length L. Okay, so I'm going to use the definition of charge density, which is lambda, and in our case it is charge per unit length, GTH. I'm going to say, okay, it has charge Q enclosed. So what I'm saying is that if you think about length L of this line charge, that length L has Q enclosed amount of charge in it. Okay, and length, that means that I must have a denominator capital L. So this implies that lambda equals to Q enclosed, lambda times L equals to Q enclosed. Okay, now I just use this in this equation and I get E times 2 pi L equals L lambda over epsilon naught, and if I solve for E, I just get E equals lambda 2 pi r epsilon naught. This is the answer. So quick recap. We established that the electric field must be perpendicular to the line of charge here. To establish the electric field must be perpendicular to the line of charge. Then we said that, okay, if it's perpendicular to the line of the charge, that means flux through the sides will be 0. So all I have to do is calculate the flux through this Gaussian surface, where the area vector and electric field, they point in the same direction. That means theta equals to 0 and cos 0 equals to 1. So I just did this, use cos theta cos 0 equals to 1. Area enclosed will be the curved surface here, so I have 2 pi RL. And then I use the definition of charge density, which is charge per unit length, to calculate Q enclosed in terms of lambda and L. And I use that formula right here to solve for E, and I got this answer.